Hello everyone, this is Ron. I'm glad to be here to introduce something to you. Okay, today I want to introduce the simulated annealing algorithm to you. Simulated annealing as a algorithm is a heuristic algorithm, and it could be used for optimization. It has been proposed for many years. I think it's about for the first time it was proposed in the year of 1950, in the 1950s. So it would be old algorithm, but it has been widely used in different applications. So today I want to introduce this algorithm to you. Okay, let's jump into it. First, what is there are two core ideas about the first is the two core ideas about the SA. One is called the annealing process. Yes, it is the process of the physical process, and it's about a heated object, a heated stuff which is heated like a physical metal block, and when it's heated, and we will be annealing to the atmospheric temperature. This process is called annealing. And this process is we just design the simulated annealing algorithm by simulating this physical process. This is a way to design the algorithm. Another kind of idea is the metropolis criterion. Yeah, this I will show you the details about the metropolis criterion and the two kind of ideas. So what's the first? I want to say what is the annealing. I want to tell you something about the annealing process. It is easy to be explained. So what is called the annealing process? I told you. Annealing algorithm is, for example, this is the stuff or the metal. First it will be heated like this. Like this. I mean, this is the particles. They are. I mean, it represents the energy. I mean, the potential, and when it's be heated, the particles will be chaos. Will be very chaos and irregular, like this. I mean, the particles will be jumped and will be active, and the inside the structure or the perturbation will be very mass, will be more mass. But this is called the initial state. This is the heated, and this is cooled down by annealing. Next, when it's cooled down by annealing process, I mean the particle will be permuted in a very regular way. So at this moment we can see the potential or the system energy is at the lowest. This is called the annealing algorithm. So the physical theory, the system cooled down by the annealing has the lowest energy system has lowest energy. This is why we use this way to design the algorithm, because we can use the energy to represent our fitness function. Yes, and we want to get the optimization, and for algorithm or any other optimization algorithm, we want to use this to, we want to first we do the iteration, just iterate it. The variable will be updated. How to update the variable? It's very easy. Just simulate the annealing process, and then we get because we think the system cooled down by the annealing process have the lowest energy system energy, and we think, okay, we get the fitness reached its convergence, so we get the optimized solution, and the corresponding variable of the lowest energy will be the best solution, the optimized solution. This is the idea we use this way to design the algorithm. And this is in thermodynamics and linear. And so this is why we designed the algorithm in this way. So we need to do cool down. How to cool down? Cool down means the temperature. T means temperature will be, for example, this is the one way to design the cool down, to design the linear. The x, this is T means there is alpha, and the constant which is smaller than 1, and it's and so every time the T will be updated, and by this way the temperature will be like this. The temperature will be cooled, will be reduced. So it's like the way the temperature is the iteration. Every iteration will repeat this using the formula, so the temperature will be decreasing. So this is the way we cool down. So this is why. So when we reach the lowest temperature, the system will tend to be the most regular and have the lowest energy, and the energy will be our fitness. And just do this process using a linear algorithm to design the optimization algorithm. This is the core idea of the linear algorithm. Why, and also the reason why this algorithm is called the linear process. The second kernel idea is the Metropolis criterion. Metropolis is the name of the inventor who invented the algorithm. I think it's a scholar, the name of the scholar. So what is the Metropolis criterion? How to explain this clear? First, we need to explain the hill climbing searching. What does that mean? What is hill? It's a way of grading searching. What does that mean? For example, giving an example. For the example, there is a function. The horizontal axis is the x, the variable, and the vertical direction is the fx, is a function. Okay, is the fitness. Okay, we know this. For example, have some peaks and valleys. For example, maybe no, it's not good. Not my design. I want to show you something like this. Okay. For example, we want to get the maximum, and we all will know this is the maximum, and there are some local maximum. But for example, first we follow the heating. It's a hill climbing searching. First, we give it a initial value. For example, x0 means the initial variable. Like this. For example, we will do search in this direction. Yes, we'll get from every time. The x will be updated in this direction, and we get the best, a better solution, but over there, and we found in the neighborhood this one is the best, so we will not accept the x over there. So the greedy algorithm, the sort of greedy searching is we just accept the better solution and reject the worst one. That means for in this direction, okay, over there, for example, this variable is a, so we will get over a here. For example, this is the iteration. For example, okay, we will get the fx will be good until get a, but when over a the neighborhood and the solution will not be accepted because all of them is worse than the fa. So we will not over this. So because of this, when over this, this process will repeat for many times. We will think it has reached its convergence. So we will think fa is the optimization, but apparently the FA is not the low global optimization. Yeah, FA is just the local optimization. So the shortcoming of the disadvantage or shortcoming of the climbing hill climbing algorithm is easy to reach local optimization, and two is sensitive to initial values. For example, here x0 is over there. For example, okay, we think okay it's bad, but for example it's over there. Yeah, we think yeah in that direction we can easily find the maximum optimization. I mean the global optimization. This is the global optimization, but over there, okay, that's also bad. So usually we set the initialization of the x as using the randomness. So we don't know the quality of the initialization. So it's sometimes it's bad, sometimes it's good. So it's very sensitive to the initial values. This is another disadvantage of this method. So to overcome the disadvantage of the hill climbing searching, the policy of the metropolis criterion is proposed. How to that means? What does that mean? Okay, for example, fx, we have fx, okay, and fx is the new value of x, for example, and fx with this is plus and fx. So if fx larger, for example, over there, like this, new photo, okay, like that. For example, over here, fx is fx plus. If x plus over is larger than this, okay, we think okay we'll accept the due value because it's much better. Certainly, we will accept this because we want to get the maximum value. So we'll accept this. This direction is good. But however, when the is not larger, it's not greater than the previous one, in the hill climbing searching, we will reject this. We'll reject the lx plus because we think it's better, it's worse. So why should we accept you? Because you are worse. You are the worst one. But in using the metropolis, we will use the probability to accept this. That means, for example, the design is like this. We will if the e is the exponent constant with the power of minus df over t, is greater than the randomness. That means a random number in the range from 0 to 1. If this is larger than this, we'll accept. Sorry, it's x. That is this. I want to write it clear. Okay, okay, we'll accept this. Otherwise, it will be rejected. This uses a way to like this. Also, the df means f, the new solution of the difference between the new solution of the solution and the function of the old solution. Yeah, like this. It's like this. We'll use a probability to accept the new solution by this way. So there is the probability. So that means what? It means like this. For example, over here we know there's x, and here is another x plus a new value. But we know certainly here the f x, the new value x plus is worse than the previous one, but we will use the probability to judge if we judge this. Now in the hill climbing algorithm, we will reject it, but here we use the probability. Maybe it will be accepted. When it's accepted, we will get another search, or maybe over there, searching. here, this one is greater than this. So, and when we get this value and this value, maybe there's a probability that we will give it a probability to get out of the local optimization, like this. Get out of the trap. It can avoid the trap of local optimization. This is the way why we do this. And also, because we will do this many times, so the initial solution, the initial initialization is not that important for this algorithm, because over 0 we can jump to 0, and if we give it 0, it's good, and we will also jump. If we give it 0, we will reject, and we will update this. And so the initial solution is not important anymore. That's also different. So the metropolis criterion is a policy that can help us avoid local optimization and the sensitiveness of the initialization. This is the two advantages of the metropolis criterion. So we know the criterion, metropolis criterion, and the annealing process, and two kernel ideas about the simulated annealing algorithm. Then we will see the procedure of SA based on the metropolis criterion and the annealing algorithm, or the annealing process. Okay, I will show you the process of that. Okay, all right, it's smaller. Okay, first is the optimization. Is optimization. Is initialization. And first the T max. I think T max. I mean the largest. I mean the largest optimization. The temperature. And the T minimum is the to judge the convergence, or when the cool down, what's the final temperature is given by the T min, means minimum. The S here is the variable, is X in this example, but here we use another sign, use S. And iter means the number of cooling down. How many times of the cooling down? Okay, so we'll give it a number. For example, certainly at the beginning it was 0. And then we'll do another thing, is the K. So we give it a rectangular. Okay, we contain everything. Is a K means 0K. What is the K? K is K. What is the K? K is the is a counter of searching. The counter of searching numbers. How many times it would be it would be searching at a specific temperature. For example, we will T initially we give it T, and then it will be T, and will be cooling down, will be decreased, and at a specific temperature, how many times will be searching, like this. Every time it will be searched for several times, and the maximum we'll give it L. L means the maximum searching time at a specific temperature. Yes, it will be using as a convergent condition. Okay, and then we'll use a way to generate a new solution. A lot of ways can generate. For example, S means plus random. Yes, random. For example, give it a range. It's like way. It's just an example. We'll show you some details about this way, how to generate the new solution. We get the new solution, and we will get the df. Df means fs plus and fs. F means this is the new solution of the fitness function. F is the fitness function. It's the optimization objective which will be used in the algorithm. and then we can get df. df will judge, use the metropolis criterion to judge if the situation about the new solution will be accepted. First, the df here is not here because we want to get the, usually in the procedure of the standard procedure, we want to get the minimum. We want to search the minimum. Here we give the example to search the maximum, but here we want to using the standard of the procedure, so the minimum we used. So we want to judge if the smaller the variable corresponding to a smaller fitness function value will be accepted. It's not that different because just give it a minus in the objective function. So that's the same. Okay, so here we use this one. Okay, we use this is that means is when the is more good, is better, the variable will be accepted. When the acceptance is not better, for example, the df greater than 0, that means the new solution is worse, and we will use the metropolis criterion, use this way to random 0, 1 to judge if the accepted. Perhaps it will be accepted. If yes, that means we will accept the new solution. Okay, we will update the solution. And if no, okay, no, here is like this. We'll judge the convergence condition of the algorithm. For the convergent, okay, first is if t, okay, sorry, it's like this. Is smaller than the Tm. That means we have reached the coolest temperature. So that means, okay, another is okay, the fitness f has repeat for several times, for many times. Means the repeat for many times. So that means the fitness function like this. Fitness function, okay, it's like this. It doesn't change anymore. So we think it's reached This is one commonly used way to judge the convergence. For example, give for many times. Okay, we can give it a number to quantify this. And if no, yes, certainly we will get the algorithm ended, and we can get S star, means the optimized value solution, and then if not, K will plus 1 because because the searching will search many times. Yes, search many times. We'll judge H. K is smaller than the L. That means if it's smaller, that means it's for a certain temperature. The searching process is not ended, so we need to still do the searching process. We're searching it for many times until K is equal to L. L is has been initialized. Yes, maximum for searching. This is like this. Okay, so if K, so then we will do this. Give it a new value and do searching. So if no, that means we'll do the cooling process. T will be T new. How to update T new? I will give you more details. That means a lot of ways to cool the T new. So and then we'll get the it will be plus 1 because means we do one cooling down process, and then we'll go back to the K 0 because another we have searched many times in one temperature, and then when the temperature updated, we will do the searching, repeat the searching process. The L times should be searched, and then finally repeat the process. We will get the conclusion. We will get the solution. Okay. And here we have no two undetermined things. one is new solution, how to determine this is one, and another is how to design how to design the way to solve this problem, to cooling down how to decrease the temperature. There are a lot of ways. Just to give you some examples. For example, one way for the how to say the data the due solution generation. One, for example, there are some ways. For example, for example, we can get this STD. We can is the standard. STD is the standard variance. And we can get this to judge to get the minimum between the square root of T, temperature, a specific temperature, and the upper minus lower. That means upper is, for example, is the solution is the upper limit and or the lower limit of the solution. For example, it's A, B. Here we can get this. We will search in this range. Okay, upper and B, and minus learning rate. Learning rate is a predetermined constant. Okay, and then we'll get the smaller value. Then we'll give the y will be normal function. Normal distribution is a Gaussian distribution. The mean is 0. The standard derivation is STD. Okay, and then we'll get the x new like x old minus learning rate. As mentioned, the learning rate is a given constant and y. So we use a way to update this. It's one way. Another way is we give it a u is uniform, is following the uniform distribution from minus pi over 2 and positive pi over 2. Okay, so not like this, not included. And we can get xc means learning rate. Okay, and learning rate is the same as it was before, and it was a constant, pre-given constant, and the learning rate, and times t is the temperature and the tangent of u, and we can, okay, so we can get this, and the x new is x old. You see, it's a two-way of this. Okay, now I just want to give you some example. And another is the how to update the T. It's one way, two-way. It's two-way. You can choose one, not just a design. Just an example. Some commonly used methods like this. How to cooling down the policy, for example, is a lot of ways. First example is like, okay, T new is a T. Okay, it's a log. It's a logarithm function. Iter is the cooling down, the number of the cooling down, and another is T means no log, just use the real number. Okay, the two ways of do this. There are some examples to do this. You can use one, use two. You can, or it's a combination of this method, and you can achieve this. Actually, it's just not a very different. Maybe it depends on your problem. So as last, you can use this way to design, this way to get out of this. Yeah. Okay, that is what I want to show you, the process of the simulated linear algorithm. Thank you very much. Thank you for listening. And I think what I told you is very clear. So maybe you can scroll the video to check the whole process of this flowchart diagram. And thank you very much for listening. And if you have any problem or any question, please let me know. Do you have any comments on my video? Also, please let me know. Thanks very much for listening. And your comments and your question will be very welcome. Thanks very much.